All right, welcome back once again. In this presentation, we're going to look very carefully at exactly how the computer sets up various types of cache memories and how requests for access are turned into requests to look into cache memory for that particular byte that's being looked at. So let's start with a big overview, and then we'll keep zeroing down into the details here. So remember, we have our cache memories on the CPU chip. Right now, we're not going to worry as much about whether it's level 1, level 2, level 3, because what happens works the same at all those levels. So we're just going to think about it as cache. And then we have our CPU has access to main memory. And here I've shown it up and down the side of the screen here because it's important to recognize how much larger main memory is than cache. This is a very important concept. And when you recognize that, it makes it easier to think about certain things and even whether you're getting the right answer for some things later on that you're going to be asked to do after this particular presentation. So just remember that huge amount of memory here. That's going to come through over and over again as I show you things here. So now we had seen a picture like this previously, with the idea that we've got some main memory here. It's really quite large, and we're going to separate it into blocks. Now in this case, the blocks are going contiguously this way as we look at this particular picture. And up here we have the cache. And in this case we have 4 sets, and we've got 2 of these what are called lines. So an extra spot, if you will, per set to hold on to whatever memory maps to that set. And the mapping indeed is like this. And you can see here that in this current point in time, the memories whose numbers were 4 and 8, the memory blocks, map here, and they're both now in the cache at this point in time. So we have some important pieces of information here. The number of sets, which is in your book designated as capital S and often designated this way in other documentation you might see. The number of lines here is 2. So there's 2 lines, this kind of 1 extra spot to hold the blocks that map to that set. Now, as an example, suppose every one of these blocks was 32 bytes. And we know that we have 4 sets here. So in this particular case, our cache is always the number of the size of our cache. The number of bytes in cache is always the number of sets times the number of blocks in, the number of bytes in one of these blocks times the number of lines. So number of sets, number of bytes in a block times the number of lines gives us the size of our cache. So if B, the size of our block, was 32 bytes, which is the same size in both main memory and cache, those have to match. And in that case, this size of cache can be computed. And so if we had 32 for B, E is 2 and S is 4, that turns out to be 256 bytes. And so this is going to be an important little calculation that you're going to need to use later on. So just remember that. This is kind of a key thing. This is how you can figure out. You're often given the size of your cache C, and maybe the block size and the number of lines, and then you have to go back and compute, well, how many sets does that refer to? So you're going to be doing that later on in the activity that follows this presentation. Okay, so now again, this is a fixed mapping, so we always are going to map our blocks of memory to a given set in cache. And this is decided ahead of time, and it remains the same for every computer once you know how much cache you have and how much main memory you have. The only time it would change is if you add main memory to your machine, because the CPU on the cache cannot be upgraded. It's whatever it is when you buy the CPU. Okay, so now what we're going to do is we're going to take this picture, but we're going to twist it around a bit. And so the first thing that I'm going to do is I'm going to turn it sideways like this, so that we have our memory on the right here now and our number of sets on the left in our cache. And then I'm going to flip things around. So notice how 4 and 8 are on the bottom, and those correspond to our, our first block, our 0th block of memory is right here. So I'm going to flip this around. So we're going to put the cache so it looks like this, and we're going to flip the memory around so it looks like this. So now you see the lowest block of memory is right here, the next block of memory is here, and so on. And so now this picture is getting closer to the pictures that you will see in your textbook, and it enables me to do a few things by putting it, flipping it around like this. So here is our set 0, here's our set 1, here's our set 2, and here's our set 3 if we have 4 sets like this particular example. And then the mapping is going in this direction now. So the number of lines that we have here, E is equal to 2. And so now let's take this picture, and it's going to be the same sort of picture but generalized now. So now I'm going to generalize it to this. This is a new view. We still have our sets here, our cache sets, which is smaller compared to our main memory. Here's our set numbers, but I'm doing it generically as if we might have more than 4 sets. Now, one thing that's interesting is if you go and try to look some things up on the web about this, you might see the term K-way associative cache instead of, your book uses E-way, and E is the number of lines per set. So just, if you go and look, and then even you may hear me say K-way once in a while because I forget, because that's the term that I'm a little bit more familiar with using. This E is something that your textbook uses that I haven't seen in all literature about this topic. So just be aware of that. But E now is our number of lines per set, and I've shown a generic number of those as well. Okay. And so now we've got our memory addresses showing up like this. So if our block size is B, the addresses from 0 to B minus 1 are going to be in this block. And then from B to 2B minus 1 are going to be in this block, 2B to 3B minus 1, and so on. And so our memory contiguously now in this picture is going in this direction. So one after the other, this is how our memory is lined up. And this is just so we can show it a little bit easier and show how this mapping works. And then, of course, this goes on and on. There is way more main memory than I've shown here. Now, the next thing to think about is, well, what is the sort of general set of bytes in any particular block? And so the address numbers that fall right here now are going to be S minus 1 times B. You see, this is the number, this is S minus 1 set right here. Here was set 2, right? So S minus 1 times B up to S times B minus 1. So that's the addresses of the bytes themselves in main memory that fall there. And so now we can see that the start of this next block up here is at S times B, and the start of this block is at 2 times S times B, and so on, all the way down through our main memory. So that's how we can think about mapping this out. So now that we have this picture, remember now, main memory is huge. So there's far more blocks here in main memory that map to the small number of lines of cache in a particular set. And what we do with this is we go ahead and set up these tags. So I talked about this in an analogous way in the last presentation. This is what we mean here. We're going to add a tag to every block all the way down. And you can see here many, many tags because the memory is going to go on and on and on. We have gigabytes worth of memory versus, you know, a small number of blocks that are here in our cache lines in one set. So we're going to have many of these tags. And so this is kind of a key point. You're going to have to recognize that when you're deciding on a tag number, you're going to need far more bits to decide to represent that than what you're going to need for the set or the block offset. So kind of keep that in mind. So each of the E lines corresponds to a different tag memory block that might be there at any time. So any of the blocks here with any tag might be over here at any point in time. And so, for example, if your code wants to access some byte in this block, well, this block at set S minus 1, tag 1, might be stored in this line. It could be stored in one of the other lines, so it could be any of them. And then if your program is accessing this block, it might be stored at, set 2, tag 2 might be stored right here. It could be stored in one of these other ones, though. So it can be in any of them. So that's the basic idea here. So each line corresponds to a different tag that might get stored there at any time. And that's one of the key points here. Okay, so with this in mind now, we want to recap this a little bit. We've got the mapping to main memory to cache sets is fixed. It does not change. If you add more memory to the machine, you basically would just have more tags out here because you'd just be adding more memory. And so that's what would change, is that more memory would make the tag structure change, and then that would be stored in the computer and used from then on. Okay, now there are two types of cache. So one of them is where E is 1 and you don't have sort of these backups. And then that looks like this. You just have a single line in each set. And then the other type is called associative cache. So when E is 1, that's called direct mapped. And the other type is called associative, where E is some number more than 1. And it's also called K-way or E-way associative cache. And that's this example that I've been showing you so far. So now let's think about this. So we've got this idea that we're going to be able to map blocks of main memory with tags to particular sets. And so if we are using the associative type of cache, where we have more than one line in the set, then the actual cache block looks like this. So it has not only the data from a block in memory, but it also has the information about which tag it is, because remember, any tag could be in any one of these blocks. And so there's a little bit of information about which tag is stored in cache at that moment in that line. And there's also this interesting thing called the valid bit. So what this does is indicate whether that cache block has valid data, whether the tag is correct and the data in the block is correct. Now, typically, these will get set invalid at the beginning of your program. And also when your program completes, sometimes the cache will get wiped out and declared invalid. These blocks here are the actual block data. And so these are your B bytes per cache block that are now held in the cache. Now, when we go ahead and compute the size of the cache, we just use these B blocks. We don't worry about whatever little space was needed for the tag or the valid bit at this point. So remember that going forward as you're doing some of these computations. We won't worry about the valid bit or the tag, how much the cache size is. We only will use the B blocks and the number of lines and the number of sets. Okay, so now suppose that in our program we need to access a piece of data. Because the mapping is known ahead of time, the program knows what tag in what set and where inside that block the address is that it needs. So the system knows this. So every access of an address is actually now translated into an address that looks like this. Which tag is it? Which set is it? Which offset into the block do I need to get to a particular byte in memory? And so this address now, in order to find out if it exists in cache, the system is first going to go to the right set, and then it's going to check if any line in that set has a matching tag. So it's going to start here, and then if the tag doesn't match, it'll go to the next one. And oh, these tags match. Aha, okay. So if it finds a matching tag, that's a hit. And we can go ahead and grab it, as long as the valid bit is also set. So we have to have both the matching tag and the valid bit, and then we get a hit. And then we can take the block offset over here and go down to the exact data byte address and begin getting the data from there. Okay, so that's the That's the general idea of how we might read from cache. Now, you might have remember me mentioning something about how we typically don't have um, a lot of these backup lines. So 8-way cache is very common. That's I'm going to show you that is again for the Core i9 in a while. But the reason for that is that the more of these blocks you actually have to check, the worse off the read would be. And so designers of our CPUs have found that it just doesn't help you very much to add lots of lines because then the read is slower. So we won't see a lot of caches with a whole bunch of lines. 8 is about our limit these days because we want that read to be really fast. And so that's kind of the reason why you don't see lots of lines per set. And that's the reason that the number of the number that you need here for this small e is small usually. We'll talk more about this little s and little e in a moment. So that's a cache read. Now, this is for an associative cache. Now, if we had a direct map cache where e was only 1, then the system would work like this. And these are used sometimes because they're fast access, really fast access. So you find the set you need, then you go and you check and see if the tag bits match. If they do, you have a hit as long as the valid is set. And then you go and access the block. Now, when you go access the block, it might be that your code said, oh, I want an int. In that case, then your code would move from cache into a register the 4 bytes that you need. Now, in the case of a direct map cache where e is 1, if the tag didn't match, this whole line would be evicted and you'd go to main memory and replace it. So you pay a hit in this case if the tag bit doesn't match. And so now, just as a overview again of our kind of common architecture, a Core i7 from Intel. Here's our L1 and L2 cache, and notice that it's 8-way. So this is that E equaling 8. And this is likely not to change that much on our CPUs going forward because we want this cycle access time to be fast. And that's also why this size isn't going to get very big because not only do you have to check through the 8 lines, you have to go down to the right set. And so it's unlikely that this size is going to get that much bigger either. And so you see when it gets bigger, the cycle access time does go down. And then down here at level 3, there it's a 16-way. You pay the price for the access time, but you are able then to save more cache blocks at this level, and at least they're not down in main memory. And so that's why this level of cache will take that performance hit as opposed to the performance hit to go all the way down to main memory. And here the i9, again, 64 bytes for a cache block. This is a relatively common size. Like I said, sometimes it's 32. Some of the more high performance ones, the blocks are 128. And you might want that if you're working in high performance computing where you have a lot of data. So this is a common size, but you might see smaller or bigger depending on the CPU. And then this 8-way again is our E equals 8. So when you see, what you're going to do in the activity is you're going to see this for a different Intel CPU. You're going to see this information from a specification sheet, and so you're going to want to find these things out. So remember this, when you see it called 8-way, that means E equals 8. So that brings us up to our memory activity now. So the second memory activity is asking you to do some computations. So there's really no code involved here. It's all about practicing some computations. So you're going to want this information. In the activity, I've also said where this information is in the book. We went over this idea. The size of the cache is equal to the number of sets times E times the block size. And this is always something you're going to have to realize. And you're often given what the size of your cache is. You're often given what E is and what the block size is. And then you have to go back and compute how many sets you have. So S is the number of sets. Now this little s is the number of bits you need to represent any set. And this little b is the number of bits you need to represent any block offset. And then you typically will go ahead and from those two, and knowing how much main memory you have, you can figure out how many bits you're going to need for a tag. And just another hint, remember, lots of tags. The tag number is going to be far bigger than the set or the block offset number, and because memory is so big. And so when you're doing these calculations, you will know if you got it wrong if your tag bits are smaller than your S bits. It just isn't going to happen unless you're given some very small, minuscule example. I think maybe some of the practice problems in the book are kind of like this, but I'm having you do a real one, so you should end up needing a lot of bits for the tag. So kind of remember that, and remember this particular calculation here. And that should then help you decide, well, how many bits am I going to need for my set index? How many bits am I going to need for my tag? And how many bits am I going to need for my block offset? So you've got a couple of chances to do this given another different kind of Intel processor with some different specifications, both for the level 1 cache and the level 2 cache. So go ahead and give this a try now in memory activity 2.